Okay, so now I'm just trying to decide on space. I think I'm gonna go there and then I may have to go back there. I'm not sure I can erase.
Yeah, okay.
Shoot. Okay, so there are a number of words we use to describe the Cantor set. And at this point, I want to say if you start to feel like you're lost, hold on till I start a new word, okay? So I intentionally, I remember going to seminars, right, where like the person talked for a while, and then after a while I was like, I don't know what they're saying, right? And you start to like fade out, right? So I intentionally designed this so that I can tell you a new word and we can sort of start fresh again, okay? So if you feel like you don't know what's going on, just hold on for a new word, okay? So the Cantor set is totally disconnected. Do you know any other sets that are totally disconnected? Just on intuition, what you think that might mean?
Counting set, maybe?
Yeah, Cantor sets, counting sets. So, right, the integers are sort of our classic idea, right? There's 1, and then here's 2, and then here's 3, and they're totally disconnected from each other. All right, so what does totally disconnected actually mean, and how could this be totally disconnected? So here's my intuitive idea of totally disconnected. There is space. Between the elements of the Cantor set. So elements are the things that are in it, right? So the elements, for example, 0 is something that's in it, and 1/3 is in it, and 1/4 is in it, okay? And any one of those that I pick, I can pick a quarter. As soon as I pick it, I am able to find a little space between it and the next one. Just like I can between 1 and 2, right? There's space between those. So that's what totally disconnected is. So and I'm not gonna prove all these things, because that requires a whole bunch more, okay? But I just wanna give you the ideas behind what the Cantor set can do, and how weird it is, and why it's such a lovely example. So if I pick a third, what that says is it is possible to find a little distance going either way where there's no other Cantor set guys in there. Make sense? The next one has to be separated by some distance. So they're totally disconnected. Something to think about. It's pretty weird.
Scott?
Yeah, Tom.
Didn't you say like 1/4 was in, how, that's weird.
It is.
That's really weird.
It is. Do you want to go back to that idea for a minute?
Sure.
So why is 1/4 in there? So it's certainly in the original set. And then at the next step, it's in the upper half.
But we can never actually get to it through.
That's right.
Huh.
You're right. So it flips back and forth between halves. Back and forth forever.
So it's still between something, but it's not.
It sure feels like it. I agree.
But even when we're at infinity,
That's the issue. We have to go all the way forever, right? So all of our intuition that we're able to quite wrap our head around, at least for most of us, is before we get to, quote, quote, get to infinity, right? I mean, we could go to a billion, right? We could do this forever and spend the rest of our life at it, but all of our intuition is still about things that are finite. That is one of the challenges. So it flips back and forth. It's definitely in there. And it turns out, again, I can't prove it. There's a bunch of stuff you need to prove it. I can loan you a book. I brought them in case I got confused. So, I don't know what else I can say about it, but it is totally disconnected. So I wanted to tell you some other stuff that it is, so that you can start to appreciate how amazing it is. And then if you get interested, obviously you can go do some reading and borrow a book. And come see me, and that would be fun. All right. Okay, so the next description of the Cantor set, Shall I go there?
It's up to you.
Okay, it's closed.
One.
Okay, so the first thing that we sort of talked about was cutting out the open middle third, right? So open means that we don't include the endpoints. Okay, closed is sort of the opposite of that, but closed is even better than that. Closed says that, in fact, if I take, how do I explain that? Any number outside of T infinity, then it's possible to separate it from the set. Okay, so if I have, I'll do a sort of on the way representation. Right? So here's T infinity. If I pick a number that's outside of the set, it is possible to separate that from the set. If it weren't possible, then I wouldn't be closed. Now, actually, you know a lot about this, right? You've done the idea of if you've got a fraction, can you pick a fraction that's smaller? Right, if I give you any number, can you pick a fraction that's smaller? Can you pick a fraction that's smaller than that? Can you pick a fraction that's smaller than that? Right, smaller than that. We can do this forever, right? That's the whole thing. If this guy is really outside, then he's separated from the set by something. There's something in between that one and T infinity. That's what makes T infinity closed. So, can I write that down somehow? So if okay, another definition of closed, which I think helps you understand the idea, is that T infinity includes all of its limit points, or also they're also called accumulation points. So if you pick So if you pick a point that is inside T infinity and pick any distance around it. So here's a point that's a member of the Cantor set, and I pick any distance around it. It has to contain at least one point somewhere in there that's external to T infinity, that's not part of the set.